Alright, you need to find in your notes the examples labeled section 5.3 properties of definite integrals examples. In doing these examples, we need to keep in mind two important properties about definite integrals. And the first one is that we can add them. We can add integrals in parts to get the value of the whole integral. So the property is the definite integral from a to b of f of x dx plus the definite integral from b to c. Notice how these limits are the same. Of the same function f of x dx. That's going to be equal to the definite integral from a to c of f of x dx. So if you just think of it as, a function here bounded from a to c, and this is f of x right here, that if we break it up from a to b and then add the area from b to c, we'd get the value from a to c. Okay? And secondly, that when we use geometry to get the value of a definite integral, that if we integrate from a higher number, that is, because we're used to going from lower to higher. So if the higher number is on the bottom, suppose we have 3 to 1 of f of x dx. If we're using geometry to get the value of the definite integral, because we're going from a higher x to a lower x, then that means the x's are decreasing and this here is negative. So that means we can reverse this and write it as negative times the definite integral from 1 to 3 of f of x dx. And then calculate this as you normally would using geometry. So if that area lies above the x-axis, this would be positive, but times a negative would be a negative answer. If this function lies below the x-axis, then that assigned area would be negative times a negative would end up being a positive. So we reverse the integration, the limits of integration, and you reverse the sign of the signed areas. So the negative areas would become positive, and the positive areas would become negative. Alright, so keep those two properties in mind. Alright, so the first example is we're given 1 to 2 of f of x dx equals negative 4, and 1 to 5 of f equals 6, and then we're given 1 to 5 of g equals 8. And I'm not going to write the rest of the integrand out because we know what that is. So in the first one, the definite integral from 2 to 2 of f, well, that's 0. If the limits of integration are the same, we have no area, so that's 0. In b, the definite integral from 5 to 1 of g, well, we don't have 5 to 1. We have 1 to 5. So if we flip it, we make it negative from 1 to 5 of g at x dx. And this signed value is 8 times a negative would be negative 8. In part C, we can pull out the 3 in front and flip the limits of integration to become 1 to 2. But when you flip them, you have to make that negative of f of x dx. Now, this assigned value from the given information above is negative 4 times negative 3 is 12. In part D, again, split the definite integral up at the minus sign and pull out the constant. So we can make that 4 times the definite integral from 1 to 5 of f minus 1 to 5 of g. Be careful there, that function's not f there, it's g. So from 1 to 5, this assigned value is 6 times 4 minus 1 to 5 of g is 8. So 24 minus 8 gives us 16. And part E, we're to find the value from 2 to 5, the definite integral of 2 to 5 of f of x dx. Well, I don't have that at all given in this information. You can't use this because that pertains to g. So you have to look at this and you think, well, what can I write? What equation perhaps can I write that would relate these limits in some way. So if you think about it, we could write that 1 to 2, the definite integral from 1 to 2 of f of x dx, plus the definite integral from 2 to 5 of f of x dx. That would be equal to the definite integral from 1 to 5 of f of x dx. So from 1 to 2, this is negative 4. This is what I'm finding. I'm finding this value. So this is from 2 to 5 of f. And from 1 to 5, another value is 6. So you're treating it like an equation. It is an equation. So if I'm solving for this integral, I would add 4 to both sides and get that the definite integral from 2 to 5 of f equals 10. So again, just to go over that again, I just created an equation which relates these limits, and I'm just adding them. The area from 1 to 2 plus the area from 2 to 5 would give me the area from 1 to 5. Some people also do the, with the subtraction. This is the area of the whole piece from 1 to 5, and that is 6. Minus the area of one of its parts, which is this, which is a negative 4, that equals 10. So some people could also work with the integrals doing subtraction, that the area of the whole piece from 1 to 5 minus the area of one of its parts, which is this, minus the area of one of its parts. Well, it's minus a negative 4, which would become 10. Or you can create an equation adding the definite integrals from 1 to 2 plus 2 to 5 equals 1 to 5. This is 6, this is negative 4, add the 4 and get the value to be 10. Okay, next, in a continuation, in number 2. We are given that f is continuous from 0 to 3 of f at z dz equals 3, and from 0 to 4 of f at z dz equals 7. Find each integral. So the integral from 3 to 4 of f at z dz. Well, if you look above, they both have f in the integrand, so that looks good. And they both have limits 3 and 4. So I have to think, can I create an equation maybe that would relate all of these limits of integration? So if we start from the low, 0 to 3 of f plus 3 to 4 of f, that would be equal to 0 to 4 of f. And it's really, of course, f of z dz. So 0 to 3 is 3. 3 to 4 I don't know, but 0 to 4 is 7. So then now if I subtract 3 from both sides, 3 to 4 of f of z dz would be equal to 4 by subtracting 3 from both sides. Okay? The area of the whole piece is from 0 to 4. So the area of the whole piece is 7 minus one of its parts, which is from 0 to 3, which is 3, gives you the area of the other part, which is 4. So you could do it viewing subtraction, or you can view it doing addition. That 0 to 3 plus 3 to 4 equals 0 to 4. When these are the same, they'll give you the area from this to this right up here. Okay, and then this is 3, this value is 7, subtract 3 and you get 4. In the next part it says the value from 4 to 3 of f at t dt. Well, you know everything in terms of z. So if you let t be equal to z, and then dt would be equal to dz, so this would become dz, this would become z, and your limits of integration would change, so that when t is 4, z is 4 now, and then when z is, when t is 3, z is 3. So I get the definite integral from 4 to 3 of f at z dz. So I don't have that. The previous answer is from 3 to 4. Well, if I flip these around, make it negative from 3 to 4 of f at z dz, I would get this to become negative of this answer, which was 4, and my answer would be now -4. Okay, and then next, number 4. Picture we're pretty familiar with is right here. So we got 1, 2, 3, 4, and this is 1, 2, and this is a line segment. And then we got 2, 3, 4, 5, 6, and this is down 2 right here. And that's a semicircle, and this is 7, up 1. Okay, so we're given 2 line segments here and here, and a semicircle below the x-axis. And this is the graph of g. So the first one is the definite integral from 0 to 2 of g equals what? Well, from 0 to 2, I'm above the x-axis, so it's 1/2 times the base, which is 2, times the height, which is 4. So my answer is +4. Next one, the definite integral from 2 to 6 of g. Okay, so 2 to 6 is right here. No, it's not. Let's see. 2, 3, 4, 5, 6. Yes, it is. So that's half of a circle. So that's pi r squared over 2. Since it lies below the x-axis, the area will be negative. So the radius of this semicircle here is 2 units from the center. So that's 2 squared is 4 pi over 2. But because it lies below the x-axis, it will be negative, or -2 pi. In part C, 0 to 7 of g. So that's the whole thing. So we have to break it up every time it passes through the x-axis. So that would be equal to 0 to 2 of g, plus 2 to 6 of g, plus 6 to 7 of g at x dx. And we can use the answers from the previous parts. 0 to 2 of g is 4. 2 to 6 from the previous part is -2 pi. And 6 to 7, well, that's new. That's 1/2 times 1 times 1. It's above, so it's +1/2. So that's 4.5 plus -2 pi. And that's 9/2 plus -2 pi. Now what's interesting to talk here is that the overall value from 0 to 7 of g, the overall value is negative. This is just over -6. Pi is 3.14, so about -6.28. And this is 4.5. So the overall value of this integral is negative because there's more area that lies below the x-axis than above the x-axis. So therefore the value of this definite integral overall is negative, or is negative. Now if we wanted to find the total area, then that would mean we'd have to take this area that's negative, make it positive, and the total area would be then 2 pi plus 9/2. That would be the total area. This answer is the net area, which equals the value of the definite integral. And then next, we're going to be very careful about part D. Part D talks about the definite integral from 4 to 0 of g at x dx. So anytime you're using area to get the value of the definite integral, you have to make sure the limits of integration are from low to high. They're not. So make it 0 to 4 of g at x dx and make it negative. So just remember that if you reverse the limits of integration, you reverse the sign, which now becomes negative. So just proceed as normal, leaving the negative out in front. So from 0 to 4, that's here. So that's of that triangle, which is 1/2 times the base times the height, plus this area underneath all that. So that's 1/4 of a circle. So that's pi r squared divided by 4. The radius is 2, so 2 squared is 4 divided by 4 is 1, so it's pi, but it's negative pi because that's below the x-axis. So then now this would become inside 4 plus negative pi. But because the original problem went from a higher number to a lower number, all these signs in here, all these signed areas will be negated. So when you distribute the negative, you get -4 plus pi. So, if we were to just go from 0 to 4 of this function, if we were given this, I would definitely say that the answer would be positive because there's more area above than below. But because we were given 4 to 0, that reverses everything. So therefore, it would be more negative, slightly more negative in this case. Because of the fact when these limits go from high to low, everything gets reversed. Okay, so again, just make this negative. Proceed here as normal. Anything that's above is positive, anything that's below is negative. Then when you distribute through, it will negate those areas. Okay, next is part number 5. Using geometry again to get the value of the definite integral. So from 0 to 3 of 1/2 x minus 1 dx. This one here is a little different than before. When you go to graph this one, you always put in your limits. So you get 0, -1. And then 1, 2, 3. And you put in 3, you get 3/2 minus 1. That's 1.5 minus 1, which is 1/2. So this is up 1/2. This is a line. So you have to figure out where it passes through the x-axis because that's where the integral is going to get broken up. If you connect this point to this point, you're going to pass through the x-axis. So in order to calculate this integral, you need to figure out where it passes through the x-axis. So if you set this equal to 0, add 1, multiply each side by 2, you get x be equal to 2, right here. And then when you connect like that, you get the line. So it's passing through the x-axis here at 2. And this is 1 right here. So then now the area below right here would be then -1/2 because it lies below, -1/2 times the base, which is 2, times the height, which is 1 unit long, would then be -1. Now this area right here, this is, remember, up 1/2 only. So this area would be 1/2 times the base, which is 1 unit long, times the height, which is 1/2. That would be 1/4 then. So it would be -1 plus 1/4. Make that -4/4 or -3/4. So the overall value, or the value of the definite integral, is -3/4 because more negative area lies below than positive area above. So again, the important part here is when you have crossovers, you have to do them separately. The area that's below and then the area that's above, you have to figure them out separately and then add your answers. Part B is just something to be careful of about there. You're integrating again from a higher number to a lower number. So we know that this is a graph of a semicircle of radius 2, just like that. So therefore, to say that this is pi r squared over 2, that's the area of a semicircle. The radius is 2, 2 squared is 4, that's 4 pi over 2, or 2 pi. But it's not 2 pi, because of the fact you're going from a higher to a lower, so you need to reverse the limits of integration, and we put the negative in front, so that would now be -2 pi. In part C, we've done that one before, the definite integral from -3 to 0 of 1 plus the square root of 9 minus x squared dx. You can draw it or split it up here. You can go from -3 to 0 of 1 dx plus -3 to 0 of the square root of 9 minus x squared dx. So this is of a constant. The definite integral of a constant is the constant times the upper limit minus the lower limit, which would then be 3. This is a semicircle. Well, this is a semicircle, but this from here to here is a quarter of a circle. So -3 to 0 is this portion right here. So that would then be pi r squared over 4. R is 3, so that would be 9/4 pi then. So the answer would be 3 plus 9/4 pi then. That would be the answer there. And finally in D, that the definite integral from 5 to -2 of the absolute value of x minus 3 dx. Again, we're going to use area. So the key x value here is 3. 1, 2, 3, 4, 5. That makes it 0 there. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Pick the endpoints. If you pick 5, you get 5, 2. And if you pick negative 2, you get 5. Right here. And here, if x is 0, you get 3. So there it is. Bounded from negative 2 to 5. Remember, since we're using geometry, we're going from a higher to a lower. So we need to reverse the sign and the limits of integration. So now I'm set up to go. So it's going to be negative times what? Alright, so negative 2 to 5. I'll do this right here. So that would then be 1/2 times 2 and 3 makes 5. And then that height is 5 plus 1/2, 2 units long, times 2, 2 units long, high is 2. So then this would be then 25 halves plus 4 halves, just might as well keep it as that. So to add these, you would get 29 halves, but the negative in front. So it'd be negative 29 halves would be that area then. Okay? And that concludes the examples for section 5.3, properties of definite integrals.